Okay, so we have just finished writing the fundamental theorem of calculus part 1. So let's just kind of review this, and then I will further develop this idea. So a of x was this function from the derivative, the integral from a to x of function f, and we just used t as a dummy variable, right? This was a function. What did the fundamental theorem of calculus part 1 say? Basically, it says this is a function whose derivative is f of x, right? Now, we have a name for this. We have a definition for a function whose derivative is the given function f, right? So we say ax is an what? Antiderivative of f by definition. Okay, now let's say if capital F of x is any antiderivative. You remember how two antiderivatives of the same functions differ by a constant, okay? If capital F is any antiderivative of f, then a of x is simply that antiderivative plus some constant, okay, for any function. Now we know something. We know a of b is what? This will be the integral. In fact, that's the entire integral. That's the entire area we are looking for. The integral from a to b of fx dx, right? And f of a of a, capital A of lowercase a, is the integral from a to a. So of course that's equal to 0. All right. So this is of course f of b plus a constant, and this is f of a plus a constant. Okay, and therefore look at this. I mean, if you look at the difference, I'm going to do a subtraction here, if I may. All right, the difference between this and this is the difference between this and this, and that's of course exactly the integral from a to b of fx dx. That is the area between a and b under f that I'm looking for. That is the integral. That integral is this minus this, but of course c's will cancel, so it's fb minus fa. All right, so that is known as the second part of the fundamental theorem of calculus. Let me go ahead and state that. Fundamental theorem of calculus, part 2. It's a two-part theorem. So this is the last and the second part. Right? It says that if capital F is any, now by the way, when we talked about the antiderivative or the indefinite integral, we always said we have to have this plus c, right? But because you're evaluating this twice, okay, and you're subtracting, whatever the c is, they cancel each other, just like what you saw here. This minus this, the c cancel. So it doesn't matter what the constant is. If f is any antiderivative of fx, and that is f prime of x is the given function, then we know how to find the integral of f from a to b, okay? It used to be the limit as the biggest subinterval approaches 0 of the Riemann sum. We no longer have to depend on that. In fact, we just find the antiderivative and evaluate them at the two endpoints, okay? Now, and that's it. You don't even have to worry about the limits or the Riemann sum or subintervals or partitions or right-hand approximation or left-hand approximation. None of those things is necessary in order to evaluate the definite integral of f from a to b. All you have to do is to find an antiderivative, any antiderivative, and evaluate them at a and b, and then find the difference. Sometimes we write this as f, and then A and B like this, this is the same thing. This is just a shorthand symbol of saying f of b minus f of a. And of course, I will be using that symbol many, many times. So you may as well get familiar with this. All right, this is the second part and the most practical part of the fundamental theorem of calculus. Right? How do you find the integral? Find a antiderivative. Basically, do the opposite of the differentiation process. Evaluate at the two endpoints, and there. Okay, that's it. Now, this is quite surprising. So what's surprising about this is, see, f of x, right? And f of x could do all sorts of things. It could go up and down many times between a and b. What this is saying is it doesn't really matter what happens. It could in fact go negative, whatever, right? The only thing that's necessary is to find the antiderivative or an antiderivative, any function whose derivative is this lowercase f. And the value of this integral only depends on the values of the antiderivative at those two endpoints. Okay, so the entire integral just basically can be determined by what happens to the antiderivative at those two endpoints. And so that is a powerful statement. And in fact, it's so powerful, some people call it the fundamental theorem of calculus. All right, so what would you say if I just ask you to stop and say, hey, can tell me what you think? All right, here we now have a way to evaluate the definite integral for many functions by using this anti-differentiation. I think what you should say is, wow. Okay, wow. Maybe you pause this for a moment, maybe for about an hour, and just digest this. Appreciate the wonder and the power and the intelligence, the creativity that went into proving the fundamental theorem of calculus. And you should just be awed and stand at this amazement. Okay, let's do a bunch of examples here. Okay, what is the area under the curve x square of between 0 and 1? Now, we did this before. Okay, and remember, this was the surprise ending, right? The ending happens to be 1/3. That was the conclusion of taking, I think we took the right-hand approximation of x square as we divided this interval into n subintervals, n equal subintervals, and you took the limit as n approaches infinity. We found the answer to be 1/3 using that formula for the summation of n square as n goes from I square as I went from 1 to n. That was a long process. Well, guess what? Do you know the antiderivative? By the way, when I say the antiderivative, I'm talking about the indefinite integral. Do you know functions or any function whose derivative is x squared? Well, clearly you have to have x third, but if you take the derivative of x third, you have 3x squared, which is not this, but you can make an easy adjustment here. 1/3 x to the third plus c, right? You always have to have the plus c. But when you find the definite integral, you don't even have to have that plus c because that doesn't matter, remember? So you can write it this way. So this will be 3, or 1/3 times 1 to the third minus 1/3 times 0 to the third. And of course, in all of these cases, if you have a constant, you can just take that to the front and evaluate this thing from 0, at 1 and 0, find the difference. All right, so the answer is 1/3, as we saw before. But the fundamental theorem of calculus makes the computation much easier. We also did this. Okay, so this is y is equal to x. The integral from 0 to 2 happens to be 2, right? Let's make sure we get the right answer. So what's the antiderivative or indefinite integral of x? It's 1/2 x squared, right? Whose derivative is simply x. Plus c, of course. When you write an indefinite integral, you have to have plus c. When you try to find the definite integral, you do not. Okay, so this is 1/2 times 2 square minus 0 square. and that's 4 over 2. The answer is 2, as expected. Man, so fast, right? Okay. Sine function. This is a smooth curve, 0 to 1. 0 to pi. Okay, so sine of pi is 0. So we are talking about this one mound or one hill from 0 up to 1 down to 0 as x goes from 0 to pi. What do you think the area of this function is? The area under the curve of this function from 0 to pi. Now, sine of x is remember, it's a transcendental function. It's not algebraic, right? And in fact, pi is an irrational number, 3.14, blah, blah, blah. So there is no reason for anyone to expect this area to be a nice number. Maybe it's going to be another irrational number. Maybe it's a transcendental number, maybe whatever, right? Well, we can certainly calculate this. Do you know any function whose derivative is the sine function? You say, oh, that's cosine. Wait a minute, it's not, right? Because cosine of x has the derivative negative sine of x. So if you want the sine of x, you can put minus here, minus cosine of x, take the derivative, you get negative sine, which is the sine of x, right? So this is the formula we are going to use. This will be the antiderivative negative cosine of x evaluated at 0 and pi. Now, you have to be very careful when you have a negative sign because you'll see all kinds of negative signs here. This says it's negative cosine of pi minus negative cosine of 0. Okay, that's exactly what it says. Lots of negatives, triple negatives. Okay, so what's the cosine of pi? That's -1. So you have minus -1 minus cosine of 0 is 1. Now we have a lot more negative signs. It's basically 1 minus -1. Okay, so the answer is 2. Wait, the answer is 2? Yeah, that's a very nice number. In fact, it's an integer. And there's no way you would have expected this area right here to be an integer, right? But it is. Wow, okay, so this is an amazing thing. We should just stop and smell the roses when you study calculus. This is a rose. I mean, it's a beautiful thing. Out from this transcendental function, we find the area, which happens to be not only rational, it's an integer. Okay. And do I sound excited? I may, because I am. And you should be too. All right. So here's a function. This is 0. And let's stop at pi over. No, let's just go to pi. All right, so what kind of function is this? This is a cosine function from 0 to pi. Okay, now as x goes from 0 to pi, the cosine goes from 1 down to 0 and then to -1. Okay, so what is the integral from 0 to pi of the cosine function? Cosine of x. All right. By the way, you may want to collect all of these and make a list. Okay, it's called a table of integration or table of integrals. You can do all sorts of integration problems once you have a list of all sorts of integrals or antiderivatives, right? So it's important to know not only the differentiation formulas, but the integration formulas, which are basically the differentiation formulas read backwards, right? Do you know any function whose derivative is cosine? Of course, that's the sine function. No need for negative because sine becomes cosine when you take the derivative. Plus C is required. Okay, so this is going to be the sine of x evaluated at 0 and pi. So it's a sine of pi minus sine of pi minus sine of 0, which is 0 minus 0. Whoops. Did I do something wrong? No, I didn't. Okay, it's actually this and this. Remember, one side is positive, the other side is negative. They canceled each other on me. All right, so that's the thing. Now, if you want to find only this part, cosine of x, from 0 to pi over 2, just this part of it, which is like half of this, then you could do that. Okay, and you could probably guess what the answer is, because this entire mountain was of area 2. This is half of that mountain. So you could probably guess the answer. This is sine of x evaluated at 0 and pi over 2. It's sine of pi over 2 minus the sine of 0, which is 1 minus 0, and that is 1. Okay, again, which is consistent with the fact that the area here is 2. Half of that area is what you see here, and half of 2 is 1. Okay, let's do another one. How about y is equal to x squared minus 4? Now, this is a parabola that goes down to -4 at 0, something like this, right? Let's evaluate the definite integral of this function from 0 to 2. Okay, so this will be, now remember, this was 1/3. Why am I writing this? It's all the way to the right. All right, so let's go ahead and find the antiderivative of, or an indefinite integral of x squared, which is 1/3 x cubed. I think we had this before. Yeah, the very first one, right? And what's the antiderivative or indefinite integral of 4? Clearly, it's 4x, right? So this becomes 1/4x. Whoa. 1/3 of x cubed minus 4x evaluated from 0 to 2. So here I have 1/3 2 cubed minus 4 times 2. That's the first one. And then, of course, when you plug in 0, you just get 0 minus 0, right? Plug in 0 here and 0 here, you get that. So this part is irrelevant. So this is 8/3 minus 8. Okay, so that's 8 minus 24 over 3, which is -16 over 3. Are we saying that area is negative? Well, by definition, when you say the area of a region, we are thinking of a positive number, right? So the fact that this is negative is due to the fact that this part is below the x-axis. So if you're looking for the area, then simply you take the negative of this, which is 16 over 3. If somebody asks you to find the area of this region, you would say the answer is 16 over 3. If, however, you are asked to find this integral, okay, the value of this integral, then your answer should be -16 over 3, just because the region is under the x-axis. All right, so remember that the area should be written as a positive number, even though the definite integral can be positive or negative. All right, let's try another example. This one, let's do this. This is the square root of x, the square root function, going from 0 to 1. Okay, so to do this, I have to know the antiderivative of the square root function, right? That's x to the x to the 1/2 power. So you notice here, the power rule applies when you differentiate this number. The exponent always goes down by 1, and then the this goes to the front as the coefficient, right? So what happens is I need something that ends with 3/2, because x to the 3/2, if differentiated, becomes 3/2 times x to the 1/2. So in order not to have anything here, I actually have to have 1 over this new exponent, which is 1 over 3/2, or the reciprocal of 3/2. That's 2/3. Okay, now check this out. Make sure when you differentiate this, you get x to the 1/2, and you do, right? Because it's 2/3 times 3/2 times x to the 1/2 power. 2/3 and 3/2 cancel each other, giving you x to the 1/2 power. So this will be, and we will summarize all of these in the next section. Maybe this section. No, next section. All right. So the answer is going to be 2/3 x to the 3/2 3 over 2, evaluated from 0 to 1. So this is 2/3. And then, let's just factor out this. You can do this if you'd like. So this is 1 to the 3/2 minus 0 to the 3/2. And of course, that's just 1. So the answer is 2/3. Is it okay if I say the area here is 2/3? Does it make sense? Yeah, of course. Remember, this is the inverse of x squared, right? So we knew this part was going to be 1/3 just because that's what we calculated at the beginning. This one here, right? So that has to be 1/3. The whole square is, of course, has the area 1. So this is 1/3. Then the other side has to be 2/3, as we checked with the integral. All right, so I think we can now write this general statement. What is the antiderivative or indefinite integral of x to the nth power? So we have seen this over and over here. Basically, you just have to take 1 over n. You take the reciprocal of n plus 1, and then the new exponent should be n plus 1. Because in differentiation, we subtract 1 from that n, right? Now, whenever you are not sure about an integration formula, there's an easy, very quick and easy way to confirm that or check it, right? Yeah, you just differentiate this, okay? So if you're not sure, you can always differentiate this, and you get, well, this one goes to the front, and the new exponent is n plus 1 minus 1, right? And of course, these will cancel. And so, yes, that is the right formula. Great. Are you okay with this? Well, you should be okay, but if you look really carefully, maybe you aren't okay. This is okay almost all the time. It's true for all n. And you remember, we had this power rule that is good for not just positive integers, not just negative integers, not just rational numbers, but in fact, the power rule throughout chapter 3, we found out that the power rule applies to all of the reals. So no matter what that exponent is, this is always true. Except, well, there was no exception in differentiation. But when you say something like this, you must say something, you must have a disclaimer, because you can't have 0 in the denominator, right? So n can't be -1. Now, if n is -1, this side is just going to be 0. So you have a constant function, which of course becomes 0 when you differentiate it. But here, you certainly cannot have -1 for n, because that would make this the 0 denominator. So what happens when n is -1? You have this, which is basically saying it's 1 over x dx. Or sometimes you write it this way. Okay, but we have seen that too, I think, right? Yeah, we saw it, okay? We do know a function whose derivative is 1 over x. What was it? Yeah, that was the natural log. This is so strange. Everything else so far is algebraic, except when n is equal to 1, -1, you don't have this. You don't have an algebraic expression, algebraic antiderivative. You have something transcendental. It's so transcendent that you can't reach it by any kind of algebraic operation. You have to go to transcendental function, natural log of x. And if you remember, it was more than that. It's natural log of the absolute value of x plus c when n is equal to -1. And so this turns out to be this. Okay, now we covered every exponent. We can integrate every x to any exponent, and we know the answer to that. Okay, so let's do an example of this, and then that would be the last example for section 5.3. So here we have this function, the reciprocal function, 1 over x, and let's go from 1 to 2. What's the area under the curve of the reciprocal function as x goes from 1 to 2? The answer is the integral from 1 to 2 of 1 over x dx. Now, often you will see this written as dx over x, which of course is the same thing. right? Now the answer is the natural log of the absolute value of x as x goes from 1 to 2. That's ln of 2 minus ln of 1. Can you simplify this? Do you know what ln of 2 is? I don't know. Okay, but it's a number whose, what is that? E to the, this number is going to give you the number 2. Okay, whatever this is, e to this number is going to give you 2. Now this is a number, so that e to this number is going to give you 1. But you know that number. This is 0, right? So this is actually natural log of 2. All right. Great. Review these and do some practice. It's good for you.